In this presentation, we will compare two different data structures, linked list and arrays, in terms of how much time they will take to insert a new element at the end. So let's get started. Here first we will discuss about linked list. Let us suppose this is the linked list we are available with and this is the code add at end. We have already seen this code and now we need to find the time complexity of this code. We should note that this part will take most of the time, isn't that so? All of these statements will take constant amount of time, so we can neglect their time complexities. This loop we can't avoid because this will take n units of time, isn't that so? Because here this code is for traversing the list, and we are traversing the list means we are reaching each and every node of the list. If we have n nodes, then this will take n units of time. That is why the time complexity of this function is big O of n. Obviously these statements will take constant amount of time and I am not considering them. That is why I have written asymptotic complexity and not the exact complexity. So this turns out to be big O of n. So this particular function takes n units of time. But let me tell you, I can create a different function which can eliminate this particular part, that is traversing the list. So we can actually create an optimal code which has the reduced time complexity. This is our target, of course. We should always try to reduce the time complexity, okay? Here the time complexity is big O of n. Let's see whether we can eliminate this part and can reduce the time complexity or not. So let's eliminate this and let's try to write an optimal code. Here comes the optimal code. We have this main function and here the idea is to create the linked list using add at end function from scratch. Instead of having the linked list already, we will create our linked list from scratch using add at end function. Here comes the first part. We will create the first node of the list by using these three lines of code. The head is the pointer which is pointing to this node. This node contains this data 45 and the link part of this node is null. Obviously this is the first node of the list and there is no other node. That is why the link part is null. And I'm assuming that the address of this node is 1000. So head contains this address 1000. After this we have this PTR which contains this address 1000, right? This means that PTR is pointing to the first node of the list. Now we are calling this add at end function and here we are passing PTR as well as this data 98 because we want to create a new node and we want to add this node at the end of this list which contains just one node right now, right? So here I'm calling this function add at end and you can see over here this is the updated add at end function, right? It doesn't have the traversing part, isn't that so? Here we have this PTR pointer which contains this address 1000 and we have this data which contains 98. Obviously, this has been taken from the main function. After this, we have this step, that is, we will create a new node and temp is the pointer which is pointing to this node. This code is saying the same thing, right? Temp is the pointer which is pointing to this node. Data part is updated by data, which means 98, and the link part is updated by null. After this, we have this step, that is PTR link equal to temp, which means that PTR, which is pointing to the first node of the list, is now updating the link part of this node by the address 2000. That is what we are doing here. PTR link equal to temp. Temp contains this address 2000, so this will get replaced by 2000. Isn't that so? And after this we are returning temp, which means we are returning this address 2000 and you can see over here return type is struct node star. Because temp is the pointer to a node. That is why it should be struct node star. This temp, that is the address 2000, is now received in main function, which is received by this PTR. So PTR is updated by this address 2000, isn't that so? This means that PTR is now pointing to the last node of the list. This is the idea we should remember. That is why we are successful in eliminating the traversal part of the list. Here we are actually updating the PTR every time in main function. We want our PTR to always point to the last node of the list. Let's see the other part of this code. That is, we are calling this add at end function again. And here again we are passing PTR as well as this 3. And here you can see that PTR will receive the address which is local to this function, of course. And here this PTR get updated by 2000, which means that it is pointing to the second node of the list. And here of course data contains this value 3. After this step, a new node is created which holds this value 3 and link part contains null and temp holds this address 3000. I'm assuming here that the address of this node is 3000, okay? After this step PTR link equal to temp, the link part of this node will get updated by this address 3000. And after that we will return temp, which means that PTR will now receive this address 3000. This simply means that PTR is pointing to the last node of the list. PTR is updated by the new address, that is 3000, which is the address of the third node of the list. So every time you're calling the add@end function, you're passing PTR, not the head. So that we should always see the last node of the list and we can update the link part of that node without traversing the list. This is the idea we should follow here. After all these steps, we get this linked list, and of course PTR is pointing to the last node of the list. So every time you call add@end function, you should pass PTR and not the head pointer, so that every time there is no need to traverse the list and you can simply add the node at the end of the list by just updating the link part of the previous node. This is easier and it will take less time. And of course, after creating the linked list, you should update PTR by head, which means that now PTR will point to the first node of the list, so that we can use it to traverse the list if we want to print data on the screen. Here you can see this code is for traversal, and of course after this step, the output will be 45, 98, 3 and 67. So the time complexity of this code is big O of 1. We are interested in finding the time complexity of add@end function. You should not count that while loop which we have seen in the main function, okay, because that one I'm just using to print the data. Here this add@end function takes big O of 1 time because we have successfully eliminated the need for traversal. Every time we are updating the PTR and every time we are passing PTR to this add@end function. So that there is no need for traversal at all, we always have a pointer which is pointing to the end node of the list. And in this code we are just doing two things. We are creating the node, which will take constant amount of time, and we are updating the link part of the previous node, which will again take constant amount of time. And that's it. That is why this code takes constant amount of time. Isn't that interesting? Now what about an array? What happens in case of array if we want to add data at the end? We will discuss this in the next lecture. Okay friends, this is it for now. Thank you for watching this presentation. So we can neglect their time complexities?